Okay, let's pick up where we left off. And we just answered question 3. Let's answer question 4. If Par Inc. decides to make the maximum increase in profit per deluxe bag, what will the new total profit be? Well, now we're dealing with this column, column C. And again, the range of optimality that we developed says that we can change the price, profit per bag contribution of either standard or deluxe within these ranges. For the standard from 631 to 1349, for the deluxe from 668 to 1428. So question 4 says if they decide to make the maximum increase in profit per deluxe bag, what will be the new total profit? So that means that they're allowed to go as high as 1428 and still maintain that optimal solution production level of 540 and 252. So let's make this 14.28, and we can see that our new optimal profit, or pardon me, our new total profit is 8998.56. Let's run solver again just to prove that point. Notice that 540 and 252 did not change. So that's the answer to part 4. Let me prove it to you by making this 1429 and running solver. We did that. Notice how our production levels changed. But we want to stay within the range. We're going to restore everything to original base values. Let's put this at 9, where it was when we started this series of questions. And let's rerun solver. There we go. And we get 542.52 and 76.68, which is where we started. We want to restore all base values before each question. Again, we can only do one change at a time. Question 5. If Par Inc. decides to make available 50 more hours of inspection and packaging time, what will the effect on profits? So we're dealing with row 8 here. We've got 135 hours available now. We know that we've got a shadow price of 0. Why is that? Because knowing that we have actually 18 slack hours of inspection and packaging time. We had 135 available. We only needed 117 in order to make this mix of 540 and 252. So what that really means is that if we add more hours, all that we're going to do is increase the amount of slack available. So the question says if we make 50 more. Let's go to 185. Let's rerun solver. Nothing changes, except we wound up with more additional slack hours. We wound up with 50 more slack hours. That's all that it amounted to. Let's bring this back to 135. Let's rerun solver. And we can see now that we have 18 slack hours. So the answer to that question is there is no effect on profits. Why? Because the dual value, or shadow price, is 0, based on the sensitivity report we developed here. Remembering that, again, right here, these are our shadow prices based on that optimal solution. And for inspection and packaging and sewing, the shadow price is 0. So similarly, here, question 6, if they decide to make available 300 more hours of sewing time, how much more profit will they realize? Well, guess what? We've already got 120 hours slack of sewing time. If we change this from 600 to 900, nothing's going to change. The profits will not change. The optimal solution will not change. All that changes is we wind up with a whole lot more slack of sewing hours. Let's restore that to 600 and rerun solver, and everything is back to the base levels. So that is the set of answers to all 6 questions that I've posed here, a series of what-if questions. They're similar, the same questions are posed here with the answers. And this is similar to what you're going to have to be able to do in the test for Chapter 3. So please be comfortable with that. So here's my recommendations for your preparation to study for the next test in Chapter 3, which won't be opened until the end of week 5. First, read or reread the textbook, Chapter 3 itself. Secondly, have access to the non-audio PowerPoint files from weeks 4 and 5 to help you with reference for definitional items, remembering that the tests are open book, open computer. Thirdly, make sure you're comfortable and confident with the sensitivity analysis example we just covered, those types of what-if questions, and including your use of Microsoft Excel. Be sure Solver is working on your device. That test 3 is going to have 12 questions, each one of them equally weighted, 100 divided by 12, and 3 of those questions will be definitional. 9 of them are going to be what-if questions based on a single Excel problem that I'm going to have you download from Canvas for the purposes of that test. And then I'm going to ask you questions just like the 6 I asked you right here, except there will be 9 questions. They'll be similar in concept, if you will. So I'm going to ask you a series of what-if questions based on that single Excel problem. Hopefully that helps you feel more comfortable and you're ready for that test. Okay, let's spend a little while here the rest of this week bringing you into Chapter 6. I'm giving you an early start on Chapter 6. We're going to talk today about a transportation type of problem, and then next week we're going to finish off with the 4 other types of distribution and network model problems. So we won't have a test on this for a few more weeks, but I need to get started soon. So today we're going to learn how to set up a network model using a manual method. Secondly, we're going to learn how to formulate an LP expression using the manual method. And thirdly, we're going to learn how to solve for the objective function using Solver. And we can use these similar techniques for all 5 types of problems. Today we're only going to focus on transportation. So when we deal with the first 3 types of problems, transportation, assignment, transshipment, when we do paper-based, when we draw things out, we develop a network model. We actually sketch out and draw a paper model, a series of circles and lines that represent the activities on the network. We call these nodes, arcs, and so on. And I'm going to show you how we do that. Now, these types of problems are, as well as what we're going to eventually do in Chapter 9 for PERT and CPM, are all examples of network problems. So we're going to do this by hand. Again, you could do this in Excel or PowerPoint or any type of computer graphing tool if you wish, someday should you need to do it. We're going to do it mostly by hand today. I'm going to show you some screen captures. So again, for each of these first 3 types of problems, computer solutions, we're going to use to show you how to go and prepare basic solutions using Excel and Excel Solver. Okay, this stuff that we're working on with regard to transportation design, it's real world. Here's a couple of examples of screen captures from companies and websites that do some of this. LlamaSoft, again, is part of the supply chain management software and systems product family. JDA, similarly, they do network design and optimization. These are the higher order third-party products that do this kind of work that we're going to be doing both manually and in Excel. Okay, so let's talk about the transportation problem in some more detail. The transportation problem usually seeks to minimize the total cost of shipping goods from some number of origins that each have a certain supply to some number of destinations. We'll label that as N, each with a demand of its own right. Not just they don't have destinations have demand, the origins have supply. When the cost of shipping a unit from that origin to that destination is also known. Now, alternatively, if you're the shipper, you actually might try to maximize revenue associated with transportation. But we're gonna deal primarily in minimizing. When we do these network models, and I'm going to show you the graphical method, when we do them, we refer to the circles we're going to draw as nodes, and these are the nodes for the origins and for the destinations. The lines are referred to as arcs, and they are the valid transportation routes. Thus, when we have a transportation problem with a network representation, we have 3 origins or sources and 4 destinations. We have 12 possible decision variables and 7 constraint expressions. And these are given when we have 3 and 4, M and N, if you will, sources or origins, destinations. We multiply them for the number of possible decision variables. We add them for the number of constraint expressions. Remember that for definitional purposes. Okay, so the network representation, we're probably going to have to do this for a Chapter 6 test. When I look at this and I say, how many decision variables are going to be in this problem? How many are going to have constraint expressions? Well, we have, how many sources do we have over here? We have 2. How many destinations, or n, if you will? We have 3. So the number of decision variables is given as m times n, or number of sources times the number of destinations. Therefore, it would be 6. Now, the number of constraint expressions we come up with here would be, as I just mentioned to you a minute ago in the previous slide, would be the number of sources plus a number of destinations. In this case, that would be m plus n. Okay, so how do we do this when we want to prepare this graphically? We're going to draw the origin nodes on the left side of the sheet of paper. We're going to call that the supply side, source, capacity, and so on. We're going to label each node inside the circle the number uniquely, either number 1 or A, so on and so forth. And to the left of each node, we're going to identify the supply or capacity volume. Then we draw the destination nodes in columns. So on the right side, the demand side, the flow is from left to right. We also label each of those nodes uniquely, and over to the right of each node, we identify the demand volume. Again, on the left side, the supply or capacity volume, to the right side, the demand volume. We draw arcs or connecting lines between the origins and the destinations for all those that are valid. Not all are always valid. There may be some origins that don't ship to some destinations. These are our valid distribution routes, and we want to label each of those arcs, of those lines, with the unit transportation cost associated with that route. So we use this notation. We're going to learn how to formulate an LP expression given certain data, and again, the cost, the supply, the demand, the number of units shipped, and so on. Let's walk you through some of that. Okay, so we define the objective function. Each arc forms a unique decision variable. And I'm going to give you an example of this. And you're going to want to have this reference, this page available to you. So each decision variable we define with a subscript. And we have a coefficient for each of those is this transportation cost. And then again, the number of decision variables is m times n if all are valid. Then we have constraints. Remember, this goes back to Chapter 2 type work, where we have objective functions, we have constraints. And we're defining these right up front in our transportation model, and then we can solve for that using Excel. So we define the constraints. There are supply constraints, there are demand constraints. The number of constraints is equal to the number of nodes. Again, in this example, if there are 5 nodes, then that's the number of constraints. Remember, m plus n. Okay, supply side constraints and demand side constraints. I'm going to walk you through an example to help you with that. Now, I also want to identify that there are often certain cases, special cases, where we have to make some configuration changes, but we're not going to actually do some of these for the sake of our work, for the problems we're going to evaluate. Sometimes total supply exceeds total demand, and that's okay. Other cases, demand might exceed supply. In that case, we would have to add a dummy origin value equal to that shortage amount and have a zero shipping cost and so on and so forth. We're not going to do this for any of the problems we're going to evaluate. Okay, another special case. We're usually trying to minimize cost. If you're the shipper, you might want to be maximizing cost. In that case, you would want to solve it as a maximization problem. Last special case I really want to point out to you is that there's sometimes an unacceptable route. Again, a source might not be able to ship to a destination. If we have that kind of condition, we simply remove the corresponding decision variable. All right, we're going to look at one of these types of problems, but I'm going to start with a fresh recording. Okay,